In this video now we're going to talk about cost and performance comparison between the structural design and behavioral, and we're going to look how Quartus compiler is successful utilizing the dedicated FPGA resources to optimize better performance between those two designs. So we're going to scale these parameters here for 4 bits 32 to 64 and compare between behavioral and structural. So now here we have a behavioral design, and then our parameter is set to 4, so that means that is 4 bit. And then we're going to look at the cost and performance. So let's compile all of the design, all of it, and look at the results. So now when we look at the summary, we see that the utilized adaptive logic modules LMU is 4. So it's 4 out of 32,070. So that is less than 1%. And then, so that is the cost of it. So now when we look at the performance of it, so we need to launch a time analyzer and look at the worst delay. So, and then when you go to reports, and then we need to go to a report path. So we can start a report path. So from inputs, so we can choose our inputs, or we can just choose all of it and through, and then number of paths, 10 is enough. We just need to look at the worst of it, the worst path, and then report path. Generate all corner cases. So if you see, the worst delay we have is from input y0 to the output sum of the second bit. So the first bit of y to the second bit of output of summation. So that is our worst delay, about 8 nanoseconds. And the least worst is like 4.8 nanoseconds. So that was for 4 bits, and then we need to look for 32-bit and save it, and then you need to compile the old design again. So now if we take a look at the cost of it, so you can see we are using 18 ALMS. So we are using these 18 adaptive logic modules. So that is less than 1%. And then if you look at the time of it, so if you look at the so we need to start again. Just choose it all. Now we see we have 13. almost 14 nanoseconds, and then it's from y input y to sum, and then the least delay you have is this one. So we can see it started to increase. Now let's do the last one, which is 64 bit. Save it, and then the compile design again. Now if we see for 64 bit, we can see that we are using 34 adaptive logic modules, but the pin number have almost is 42% for the pins. And then if we look at the time analyzer, so that we see we have almost 20 nanoseconds, 19.9 nanoseconds, and the least to us is 12. And now if we do the last one, which is now, so we have done all from 4 bits, 32 and 64. Now we need to go to now the n bit structural one. So what we need to do, we need to change the parameters here, and compare that to the behavioral. So one thing we must do, we need to comment the overflow bit. So we need to be fair in analyzing. So let's remove the overflow bit. And then we need to change our bit also for the def param. So here we can just write def param 1. So what this def param is doing is changing the ripple carrier adder parameter to be the same as this one we are changing. So now let us start. Now let's start. First of all, let's put this file as save it and put it as top level entity, and then compile the design. Now if we take a look at here, we can see that we have 5 adaptive logic modules. So that is the cost of it. And then if we look at the time analyzer, and then we go to the report path. The report. Generate all corners. So we can see here we have the worst delay here for the structures is 7.8 nanosecond from X1 to the carry out, and the least delay is 4.79 nanoseconds. So this is for the 4-bit. So let's try to change it to 32. And then compile the design. Now for the 32 bits, so we find out that it consumes 40 adaptive logic modules, and we have 98 pins. So for performance, so let us look at the report path and then look for all of these. Report path, generate all corners. So we can see here we have for the worst delay is 21.96 nanoseconds from control to the summation, and the least is 12.56. So that is 32-bit, and then the last one is 64. So remember, when we change here 64-bit, we change it for the ripple carrier adder to 64-bit too. And then let's compile the design again. So now it's done. Let's see at we can see that we are using 80 adaptive logic modules, which is still less than 1%, but we are using 194 pins. So we can see that the structure one, the cost start to increase compared to behavioral. So if we look at the performance now, and then generate all corners. The delay is almost 45 nanoseconds, and the least delay is 26 nanosecond. So based on this observation, so we can see that the results demonstrate that the structural design utilize more resources than behavioral. On the performance level, behavioral also outperforms structural model. So explanation of this result is that the Quantus compiler theta, if you go to the Quantus compile theta, for example, if we go to edit, so here is the Quantus compiler theta. If you look at it, we can see that on behavioral, it means that we leave all the design and how things should be designed based on the compiler. So we can see the compiler setting is balanced, while on the structural, our design maintain the same because the numbers of the ripple carrier and the AND gate, XOR gate that are inside increase when we increase the bit size. So on the next video now we'll talk about how to combine both behavioral and structural on the same Verilog file.